Hey, hello everybody. We are down to the last two topics here. The section 4.9 antiderivatives. I did upload the notes that were complete. I didn't have a chance to make a video. Here's the video if you still need it. I apologize for being late, but this work at home thing I think is getting all of us. So we're in the home stretch. We will now work backwards, taking a function f of x and finding what capital F of x function gives us that derivative. And this was from the work backwards worksheet that I had posted earlier. This process of finding an antiderivative is called antidifferentiation or integration. It's really the second piece of calculus 1. A function, capital F of x, is an antiderivative of f of x on the interval from a to b if f prime of capital X equals f of x for all x on that interval from a to b. That's a mouthful. So for example 1, find the antiderivative f of x for the function 2x. So what you need to ask yourself is, what was that original function? So we're going to use capital F of x and think to ourselves, okay, what would give us 2x as a derivative answer? And the original problem had to have been x squared. The issue with that is we don't know if it was x squared plus 7. We don't know if it was x squared minus 10 or any other positive or negative constant at the end. We have no idea. So to represent all possible constants, positive or negative, we have x squared plus c. Yes, we still use plus even for negatives because it could be plus a negative 12. So x squared plus c. Okay, good job, dude. All right. Sorry. Mom duty there. All right, back to our screen here. Well, this shares, there we go. So theorem, if capital F is an antiderivative of lowercase f, then the family of functions f of x plus c, where c is a real number, is the general antiderivative of f over an interval. And this can be written as the following. We have the integral of lowercase f of x dx is equal to capital F of x plus c. That's the general form that we're looking for. So down here in this blue table are some 4 specific antiderivatives to work with. And in my traditional classroom setting, I'd use that work backwards worksheet as kind of a warm-up for the first 20 minutes of class, and then we would have proceeded with these notes. So these are really just an extension of that working backwards. So the first one, the power rule, x to the n. This is the rule that would have worked for the first 6 on that work backwards worksheet. So the solution is x to the n plus 1 over n plus 1 plus c. That is the formula for the antiderivative anytime you're dealing with exponents. The next one's kind of special, the integral of 1 over x dx or dx over x. This is the natural log of the absolute value of x plus c. We have 2 trig functions. There are really 6 to work with, but these are 2 for example. The antiderivative of cosine of x is sine of x plus c, and the antiderivative of sine is negative cosine of x plus c. And the reason why it's negative is because the derivative of cosine is negative sine, so if I want this to be a positive sign over here, then I need to have a negative for the antiderivative. And finally, e to the x is e to the x plus c, because the derivative of e to the x is e to the x. It stays the same. On the next page, I have 4 examples to go over with you just to kind of help reinforce all of this. So solve the following integral, 6x squared minus 7 plus 3x to the negative 2 dx. So remember, we're adding exponents this time, we're not subtracting. This becomes 6x cubed over 3 minus 7x plus 3x to the negative 1 divided by negative 1 plus c. And then in the next row, we can clean this up a little bit. 6 divided by 3 is 2, x cubed minus 7x minus 3x to the negative 1 plus c. And that negative exponent, if you wanted to move that to the bottom, might not be a bad idea. It looks something like this. Great. For example 3, we can't integrate with that x cubed in the bottom. So we actually have to move that to the top before we can do any calculus. So negative 2x to the negative 3 plus 5 plus 4x to the negative 1 dx. So this first piece becomes negative 2x to the negative 2 divided by negative 2 plus 5x. Now, 4x to the negative 1, if I try to add 1 to that, that becomes 4x to the 0 over 0. But we're not allowed to divide by 0. So this is actually on that previous list we just had. It's natural log, 4 natural log of x plus c. Clean this up a little bit. In the beginning, a negative 2 divided by negative 2 is 1. X to the negative 2 plus 5x plus 4 natural log of x plus c. And then this negative exponent, I would just move to the bottom. 1 over x squared plus 5x plus 4 natural log of absolute value of x plus c. Whoopsie. And somehow that first piece doesn't seem right to me this morning, but let me just double check. Negative 3 plus 1 is negative 2 divided by negative 2. I think we're okay. An example for, to write this with the radical. If I have the square root of x cubed, that's really x to the 3 halves over 2. And sometimes students don't like that 2 in the bottom, but remember, it's really just a 1/2. So if I add 1 to x to the 3 halves, it's 5 halves. So this is 1/2 x to the 5 halves divided by 5 halves plus c. And instead of dividing by a fraction, we really multiply by the reciprocal. So this is 1/2 times 2/5 x to the 5 halves plus c. Those 2's are going to cancel out. So this is 1/5 x to the 5 halves plus c. Fractions and negatives. Students always hate that part. And finally, example 5, 1 over the cube root of x. So we need to rewrite this as a fractional exponent instead of that radical. And again, it's in the bottom. We can't do anything with it down there. So we need to move it to the top. Now we're ready to integrate. So if I add 1 to a negative 1/3, it's okay to pull out your calculator for this. It's fine. X to the 2/3 divided by 2/3 plus c. Remember, we're not dividing by a fraction. We're multiplying by the reciprocal. So 3 halves x to the 2/3 plus c. There you go. Antiderivative. So these are, word just fell out of my head. Indefinite integrals. Indefinite integrals. I've got one more lesson about definite integrals for us, and then we'll be finished. So good job. Keep it up.